Today, modern heavy industry relies entirely on the precise speed and torque control of massive AC induction motors. To drive these machines efficiently at variable speeds, engineers use a voltage source inverter. Its primary objective is to synthesize a smooth, continuously varying alternating current, drawing exclusively from a fixed, flat, direct current supply. But the hardware inside these inverters presents a severe physical limitation. The internal tower valves, typically MOSFETs or IGBTs, operate strictly as binary devices. These physical switches cannot open halfway to deliver a partial voltage, nor can they create a smooth electrical gradient. They exist in only two states, 100% on or 100% off. The physical motor requires an analog, rolling sine wave to rotate smoothly, but the inverter can only supply rigid, square blocks of DC voltage. Translating a perfect analog curve through strictly digital binary hardware is the central paradox that modern power electronics must solve. The industry-standard solution to this engineering problem is a mathematical technique called carrier-based sinusoidal pulse width modulation, or SPWM. The premise of SPWM is to translate the exact shape of a desired analog waveform into a rapid sequence of binary switching commands. This translation is not hard-coded. It requires a continuous mathematical comparison between two independent electrical signals. The first signal is a low-frequency reference wave. This represents the exact shape, target frequency, and target voltage the motor requires. The second signal is a high-frequency carrier wave. This acts as the system's rigid internal timing clock. By constantly intersecting these two specific waves, the system dictates precise intervals for flipping the physical switches. This mathematical overlap inherently encodes a perfect sine wave into a train of choppy DC pulses. To see how this encoding works, we look at the mathematical environment of SPWM logic. In the top pane, we establish the modulating signal, a sine wave dictating target frequency. Layered over it is the carrier signal, a high-frequency triangular wave serving as the timing mechanism. Because the sine wave is constantly rising and falling, the two waves intersect at varying intervals, depending on the current height of the sine wave. A physical logic circuit called a comparator continuously monitors both signals, evaluating which wave has the higher amplitude at any given microsecond. Tracking the exact milliseconds these two geometries cross paths provides the sole set of instructions governing the physical inverter switches. Scanning across the timeline chronologically, we isolate the exact moments of intersection. This creates the first logic state. Whenever the reference sine wave is physically greater than the triangular carrier, the comparator outputs a high signal. This high signal commands the upper switch to turn on, delivering a positive voltage pulse equal to half the DC link voltage. As time moves forward, the sine wave drops below the triangular carrier, instantly flipping the comparator output to a low signal. The upper switch turns off, and the lower switch turns on, driving output to negative voltage. This document shows the mathematical formulation of a vital hardware constraint. If both the upper and lower switches on the same leg turn on simultaneously, violating the rule where the sum of the switch states must equal 1, a short circuit occurs, destroying the inverter. The comparator logic strictly respects this rule. By deriving switch commands from a single alternating intersection point, the states remain completely binary and mutually exclusive. Executing this logic continuously across a full AC cycle generates dense, variable width square waves. The exact duration of every single positive and negative pulse is mathematically locked to the amplitude of the desired sine wave at that precise millisecond. With the logic established, an operational question arises. How do engineers increase the power delivered to the motor without increasing the underlying DC voltage supply?
The answer lies in a variable called the amplitude modulation ratio, or MA. This ratio is calculated by taking the peak amplitude of the sine reference wave and dividing it by the peak amplitude of the triangular carrier. When the ratio increases, the sine wave physically grows taller relative to the carrier. This shifts the intersection points outward, visibly widening the resulting square pulses in the center of the wave. Since the DC supply voltage remains fixed, widening the pulses is the only way to deliver more average electrical energy over the same time period. Decreasing the amplitude ratio shrinks the sine wave, narrowing pulses and lowering total energy output. Adjusting the amplitude modulation ratio grants engineers complete, independent control over the magnitude of the fundamental output voltage, utilizing the exact same fixed DC hardware. If the sine wave controls the output voltage, the triangular carrier controls the timing quality. This brings in a second critical metric, the frequency modulation ratio, or MF. This ratio measures the frequency of the carrier wave divided by the reference wave's frequency. Setting a higher frequency modulation ratio dramatically compresses the triangular wave. The bottom pane immediately populates with dozens of narrower pulses per cycle as the system calculates intersections much more frequently. This forces the physical transistors to switch on and off much faster, altering the harmonic spectrum of the output current in a highly beneficial way. The rapid switching pushes unwanted harmonic distortion further away from the fundamental motor frequency, isolating the noise in much higher frequency bands. High-frequency harmonics are easier and cheaper to filter out. Eliminating them protects the induction motor from excess heat, mechanical vibration, and premature wear. This graph charts the exact output voltage of the half-bridge inverter. It shows a harsh sequence of rigid square blocks, confirming that the output voltage does not resemble a smooth sine wave at all. This chaotic series of sharp digital pulses is exactly what the physical cables transmit directly into the motor terminals. If the voltage is a violently switching square wave, why does the motor rotate smoothly instead of stuttering with every pulse? The answer lies in the physical properties of the motor's internal stator windings. These dense coils of copper wire function as a massive inductor. By the laws of electromagnetism, an inductor inherently resists any sudden, instantaneous changes in electrical current. This physical resistance acts as a natural low-pass filter against the harsh voltage spikes of the PWM signal. While the voltage snaps violently back and forth, the actual current flowing through the wire cannot keep up with the changes. It traces a smooth, continuous path straight through the center of the voltage blocks. The physics of the motor naturally averages out the rapidly changing pulse widths. As a result, the magnetic fields inside the stator react strictly to the perfect sine wave encoded within the noise. The entire system functions as a translator, taking a flat, rigid DC line and converting it into a precisely controlled alternating current. A highly complex analog curve is synthesized purely through basic geometric intersections and binary logic gates. Because the amplitude and frequency modulation ratios can be adjusted independently on the fly, a single inverter can drive an induction motor at any desired speed or torque requirement. Before this technique, varying motor speed required complex mechanical gearing or massive heat-generating dropping resistors that wasted enormous amounts of electrical power. Today, this specific PWM logic is the foundational software running inside nearly every modern AC motor drive on Earth. Carrier-based sinusoidal pulse-width pulse modulation successfully bridges the physical divide between rigid DC power sources and dynamic AC loads, enabling the industrial efficiency of the modern automated world.